Welcome to The Explainer. I am so thrilled to share today's journey with you because, well, we're unpacking an absolutely fascinating breakthrough in the world of optoelectronics. We are looking directly at a recent study that explores a completely new way for our everyday devices to essentially see the invisible, specifically near-infrared light. We're going to break down exactly how a cutting-edge vertical heterojunction photodetector works. And trust me, the engineering behind this is nothing short of brilliant. So, right off the bat, here is the fundamental dilemma facing the photonics industry today. Near-infrared detection is absolutely crucial for everything from global telecommunications to autonomous vehicles and even medical imaging. But detecting this unseen world poses a massive economic and physical challenge. Like, how do we actually build sensors that can accurately catch these invisible light waves without making the technology incredibly expensive or just impossibly complex to manufacture? To answer that, here is our agenda. First, the near-infrared silicon problem. Second, designing the Mg2Si/Si solution. Third, FTD and charge simulations. Fourth, characterizing the physical device. And finally, real-world optical communication. Okay, let's jump right in. Section 1, the near-infrared silicon problem. Let's dive into this by exploring why the technology we rely on every single day currently struggles to see near-infrared light. We really have a tale of two materials here. First up is silicon. It's the undisputed king of modern electronics. It's affordable, it's easily manufactured, and it's fully compatible with our existing CMOS technology. But there's a huge catch. It has terrible near-infrared absorption. Then, on the other hand, you have indium gallium arsenide, or InGaAs. Now, this material has incredible near-infrared absorption, but it comes with massive drawbacks. It is highly expensive, and it suffers from what we call lattice mismatch when you try to integrate it with standard silicon chips. It's basically an integration nightmare. So, we need something that gives us the high performance of InGaAs, but with the affordability and compatibility of silicon. To understand exactly why silicon fails at this task, we really have to talk about the band gap. You can think of a band gap kind of like a physical wall. For a material to detect light, a photon of light has to hit it with enough energy to boost an electron right over that wall. Silicon has a band gap wall of 1.1 electron volts. The problem? Near-infrared photons simply do not have enough energy to jump over a 1.1 electron volt wall. They hit the silicon and nothing happens. The material remains effectively blind to them. Which brings us to Section 2, designing the Mg2Si/Si solution. Let's see how researchers actually engineered an eco-friendly ladder to climb over that bandgap wall. They designed a really clever vertical heterojunction structure. It's essentially a stack of specialized layers. You've got indium tin oxide on top, then a specialized Mg2Si layer, followed by bulk silicon, and finally a silver electrode on the bottom. But the real star of the show here is that middle layer, magnesium silicide, or Mg2Si. It's an eco-friendly, tunable semiconductor with a much narrower band gap, somewhere between 0.6 and 0.8 electron volts. It literally acts like a step stool. Near-infrared photons easily have enough energy to clear this lower wall. Through their testing, researchers found that making this specific layer exactly 200 nanometers thick, which, to put into perspective, is about 500 times thinner than a single human hair, perfectly balances maximum light absorption without introducing any structural defects. All right, moving on to Section 3, FDTD and charge simulations. Before heading into the lab to actually build this incredibly thin structure, the scientists had to simulate its electrical and optical properties. Picture glowing, flowing electric fields running through a supercomputer. When visualizing the FDTD optical models, it's fascinating to see how the light interacts with the device at different wavelengths. Take the 1064 nanometer light wavelength, for example. Almost all the optical absorption happens intensely right at the surface, locked inside that super thin Mg2Si layer. But when you look at how 1310 nanometer light behaves, it's totally different. That longer wavelength penetrates much deeper into the silicon device, significantly spreading out the electric field distribution. And this brilliantly illustrates the resulting charge electrical model. Remember how the 1310 nanometer light penetrated deeper? Well, that deeper penetration yields a broader but fundamentally weaker carrier generation. The electrons just aren't being knocked loose quite as efficiently. Conversely, the 1064 nanometer light, which was absorbed intensely at the surface, yields a highly efficient, heavily concentrated carrier generation rate. It proves that the single device acts very differently depending on the exact wavelength of the invisible light hitting it. So let's get into the real-world results. Section 4. Characterizing the physical device. Those simulations are beautiful, no doubt, but we need to know if this thing actually works in reality. Let's translate those 3D models into cold, hard physical performance metrics gathered in the lab. The researchers physically built the device, tested it, and the results were pretty stunning. At 1064 nanometers, they achieved a massive responsivity of 230 milliamps per watt. But here is the absolute kicker. They achieved this under zero bias operation. That means the detector is completely self-powered. It doesn't need an external battery or any power source to pull the electrons apart. The internal electric field generated by the junction of the materials does all the heavy lifting for free. Next, they tested it at the longer and, honestly, much more challenging 1310 nanometer wavelength. The device registered a lightning-fast response rise time of just 73.5 microseconds. How did they do it? Well, by keeping that active Mg2Si layer thinned down to exactly 200 nanometers, they minimized the travel time for the electrons and reduced material defects. This actually accelerated the performance by a full order of magnitude compared to older, thicker designs. So the crucial takeaway here is that this blistering speed comes with a 3.1 kilohertz bandwidth and a specific detectivity of roughly 1 billion Jones. Now, Jones is simply the metric we use to measure how sensitive a detector is to weak signals while ignoring background noise. Reaching 1 billion Jones at 1310 nanometers, and again, doing this entirely self-powered without draining external power, proves that this little 200 nanometer layer is a genuine powerhouse. Let's bring it all together. Section 5. Real-world optical communication. We're at the climax of our pipeline now. We need to see how this builds into something we'd actually use. How does this device translate invisible light into actual readable data? To prove the device works in the real world, the researchers set up a proof-of-concept communication system. It's elegantly simple, yet highly effective. The setup starts with a laser source firing a 1310 nanometer invisible beam. Then a shutter acts as a gatekeeper in the middle, rapidly chopping that continuous laser beam into discrete pulses. Finally, waiting to catch those pulses at the other end is our brand new Mg2Si/Si photodetector, which is wired directly into a computer to read the signal. Let's trace the exact journey of a photon in this system. Step 1. The computer inputs a string of binary data, ones and zeros. Step 2, the shutter rapidly opens and closes to pulse the 1310 nanometer laser, effectively turning those ones and zeros into rapid flashes of invisible light. Step 3, our new detector absorbs those flashes and instantly converts them into self-powered electrical spikes. And finally, step 4, the computer reads those electrical spikes and decodes them straight back into ASCII text, specifically the letters ZYS. Looking at the actual data flow output from that experiment is just so satisfying. Look at how crisp those current pulses are. The highs and lows map perfectly to the binary code, which seamlessly translates back into those ASCII letters ZYS. There's no lag, no lost data, and no ambiguity. This output proves unequivocally that this detector has incredible transmission capability for real-world infrared communication systems. To wrap up our analysis, it helps to look at the definitive comparison from the study. When you compare historical photodetector structures against the new Psi/Mg2Si/ITO structure, you see how it perfectly threads the needle. It hits that crucial 1310 nanometer wavelength while offering an incredibly fast 73.5 microsecond photospeed and high detectivity. And critically, it achieves all of this at zero bias, meaning zero external power consumption. It really is a remarkable balancing act of speed, sensitivity, and efficiency that older structures just couldn't master. Which leaves us with this final, provocative thought. We now know that an eco-friendly layer of magnesium silicide, just 200 nanometers thick, can effectively give standard silicon the power to see the invisible, all without even needing a battery. As this technology scales up, how is it going to revolutionize global telecommunications? Will our everyday devices soon transmit massive amounts of data, silently, invisibly, and with near zero power consumption? The foundations have absolutely been laid, and the future of silicon photonics looks incredibly bright. Thank you so much for joining me on this explainer, and I really hope this sparks your curiosity to keep learning about the unseen world around us.